We are probably not the total cause of global warming. Yes, there is an increase in CO2, but remember the oceans have to take some credit for that. Remember, we saw a bunch of natural causes of air pollution too, didn't we? Like volcanoes are really big polluters, aren't they? And do we have any control over volcanoes? No. Okay, so, you know, man does have something to do with it, but not completely. So, and it's definitely not completely our fault. Global warming will cause many animals and plants to go to extinction. And the article is particularly talking about the polar bears because they were pointed out as having a problem, and yet actually polar bear populations are on the rise. And do any of you like Tim Hawkins? I love Tim Hawkins, and I love when he talks about the polar bears, and you know, if you see a polar bear, don't go up to him and think you're going to have a Coke. He looks at you and he goes, "Run." I thought, yeah, because otherwise they'll eat you and then they'll wash you down with a Coke. I'm like, yeah. So, but the animals are not going extinct from the global warming as far as we can tell right now. And are the oceans actually drastically increasing? And even the people that believe in global warming said they only expected 16 inches in the next century, and yet we're seeing that that's not actually happening. And that's what that newest study is about, is that they're not seeing it even though they were expecting it. Will it cause global catastrophes? That's what they say, but we're not seeing evidence of that or supporting evidence for that. So what could be causing the increase? Well, you know, your book went over this, that there was a little ice age in the past. Did you get that? And it wasn't that long ago, was it? There was a little ice age from the 9th to the 14th century. So that would be 800, I know I have a marker, hang on. From 800 to about 1300 AD. There was a warming trend, and then from 1300s to the 1800s, there was a cooling trend. So this was warmer, and this was cooler. I can spell. I've had a hard spelling day. Okay, now, trick is this. We're blaming the Industrial Revolution, when we started burning more stuff, for the increase in CO2. But the Industrial Revolution doesn't start till after this, okay? And so it's actually been cooling, and I think this went up to 1880, if I remember correctly. Okay, well, I think it was around 1880. So it's actually cooler in the Industrial Revolution time. Now, I don't know, I don't think you guys read this, but they think that it's actually connected with the sun. What they've seen is that the sun goes through periods of sunspots. And I don't know about you, but I would think sunspots, that's cooler areas of the sun. Yeah, but when there's sunspots, around the sunspots are solar flares, which are much hotter, and they make up for the difference. In periods, and the sun goes through periods of like every 11 years, it has a cycle of sunspots and stuff like that, and then there's a bigger cycle that's longer. Well, the trick is this, when we see a lot of sunspots, then the sun is a little hotter and the earth is a little warmer. When we see fewer sunspots, then the sun is a little cooler and the earth is a little cooler. And they've seen a connection with this when and believe it or not, people have been counting sunspots for a long time. And they've seen a connection with this, so they're starting to think that it actually, the temperature of the planet actually has more to do with what the sun's doing than what we're doing. That would not surprise me, considering that's what warms us in the first place, right? So anyway, okay, so over on page 40, it shows us a graph that if you make a 20-degree change on the left side, you see that the line just kind of goes bubble, 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 bubble along the middle. There's really no change. That's what they're showing us there. And so the actual change is about 1.6 or 1.7 degrees Celsius. It's not what most of us would consider global warming. Okay, on page 41, 2.7. One popular thing to do in American politics is to note that many of the past few years have been some of the warmest ever recorded. This is then used to support the idea that global warming is happening. What is wrong with this kind of argument? What's wrong with that argument? Who wants to help me? George.
The area that they recorded is just one area. It does not represent the entire planet as a whole.
Very good. If we're saying, okay, well, it's hotter here in the United States this summer, does that the United States represent the whole world? No, absolutely not. And also, the planet goes through these trends. So we would see that anyway. If there's a lot of volcanic activity, the planet cools down because you have gases that actually shoot the sun's warmth back into outer space being blown into the atmosphere, and so it actually cools the planet down. So we have all these different things that could affect. Thank you very much. Then parts per million. We're told the number of molecules or atoms of a substance in a mixture for every 100 molecules or atoms. Do you know how a percent is parts per 100? Parts per million is just like a percent to the million. So it's the parts of something per million of something. That's all. That's all parts per million is. Now, do you have to really understand that? No. What you need to know is that 1% equals 10,000 parts per million. That's what you have to have memorized. And the reason you have to have it memorized is you have to be able to do the conversions. That's a funky one, isn't it? So you have to be able to use that as a funky one. And so look on the next page, on page 42. It says the concentration of argon in the air is 0.9%. 0.9%. And it says, what is it in parts per million? So you go 0.9% times line. This is here, so it goes down here. You're trying to get to ppm, so it gets on the top. You know that the 1 goes with the percent, and you have this memorized. The 10,000 goes with the parts per million, and so then you would just use your calculator and get your answer. Okay? And then the opposite one is right next to it. Convert 11 ppm into percent. So if we have 11 ppm, and we want to know how many percent that is, we would do this. This gets a 1. This gets 10,000. Remember, this cancels. That looks familiar, right? And you'd use your calculator and you'd end up with the percentage. Okay? Any questions on that? Are we okay on that? Okay. Now, then we get to the ozone. How does the ozone help us? What does it do to help us? Yes, Caleb.
Blocks the UV rays.
Very good. It blocks out harmful UV radiation that comes from the sun that would hurt us otherwise. When I worked in cancer research at the University of Florida Department of Comparative and Experimental Pathology, which was a part of the vet school, I worked in tissue culture labs, and we didn't want things growing. We were doing cloning of things and stuff, and we did not people, don't worry. And we didn't want things growing where our clones were worked on. So whenever we got done working in an area, we would swab it down with alcohol, we would close it so no air could get to it, and we would click on the UV lights. And the reason we would click on the UV lights is it would kill anything that was still in there. Well, that would happen to us if God didn't give us a filter. And so God gave us the ozone layer as a filter. And it's very hard to filter light because it's not like filtering something else, is it? So it actually filters the energy. The ozone actually absorbs the energy. And it's interesting because, remember, oxygen that we breathe is O2. And those represent bonds of shared pairs of electrons. Ozone is this. So what happens is this bond absorbs the extra energy and is broken off, and in the process it's removed, and breathable oxygen is left behind. And then this is free to get together with another oxygen. So actually, to restore the ozone layer, there's the Chapman cycle, which they don't go into, to actually recycle the oxygen and put it back into the ozone layer. Where's the ozone layer? Because if we breathe it, it'll kill us. So where's the ozone layer? Where did God put it? In the atmosphere. Good. It's up in the atmosphere between about 12 and 18 miles, but it's up there a ways, so we don't have to worry about trying to get into it by climbing up a mountain or something, do we? Okay? So the ozone layer is very, very important. It takes away that energetic light that would kill our cells otherwise, and God put it up there where it needs to be. Okay, now, he asks a question. Go to page 44, and on that question it says, one evolutionary theory of how life originated on planet requires that at one point there was no oxygen in the atmosphere. This theory, of course, assumes that the first life form did not breathe oxygen. Since there are organisms today that can exist without breathing oxygen, this is not as fantastic as it may first sound. Based on what you've learned in this section, however, what serious objection can you raise against the theory that life originated on Earth with no oxygen in the air? What's the problem with that? Yes?
Well, no oxygen means no ozone, and no ozone means everything dies.
Good, because the UV light can get through and kill everything. Very good. Fry everything. Thank you very much, Clay. Okay, let's see. So then we get to air pollution. Why don't you turn over to page 47. It's got a picture, sort of. It's got a graph, a bar graph. There's many different types of air pollution. Sulfur oxides, nitrogen oxides, ozone, ground level ozone, carbon monoxide, and then he goes through and explains some of these. He says that sulfur oxides are formed from burning coal that has impurities in it. And so they've tried to clean things up by getting them to put scrubbers on these places that burn this coal, and then that way it can take those sulfur oxides out. But then the cost is passed along to us when we clean things up that way. But I think it's worth it to get cleaner air. And so that's the kind of thing that we have to decide. But then we're also told that that's human-made sulfur oxides. Volcanoes make enormous amounts of sulfur oxides. And let's be honest, we can't control the volcanoes, can we? So they're going to make them. And then nitrogen oxides, remember the air around us is 78% nitrogen. So when we have anything hot, like a lawnmower or a car motor or whatever, it produces nitrogen oxides, and that's also a form of pollutant. Lightning bolts produce them. Volcanoes produce it. Biological decay produces it. Oceans emit it. So there's a lot of natural sources of this one too. And then ozone is produced by cars and by lightning. So once again, we have our source and then a natural source. Airborne lead was from burning leaded gasoline. And they've taken the lead out of the gasoline. Now, have you ever noticed at the gas pump it says unleaded gas? Have you ever seen that? That's because they didn't take the lead out of the gasoline until the 1970s. Now, on page 47, you see that. Everybody sees the bar graph there? Okay. On the left-hand side, you see what it looked like before at 1975, when they started to get them to clean up the air and change things so that they would clean up the air. And then the bar on the right-hand side is 2002. It shows you the difference. What has happened to the amount of airborne lead? Has it increased or decreased? Mm-hmm. Yes, it's almost gone, isn't it? That's because they took unleaded gasoline. Cars don't burn unleaded gasoline anymore. And so that's how they handled that problem, is they removed it. The sulfur oxides also has decreased. Look at all these different types of air pollution have decreased, except nitrogen oxides are still the highest ones there, aren't they? Now, I got married to my husband in 1983, which is what, 8 years after this. And I remember going to Mexico City on our honeymoon. We went a couple places, but we stopped there because I wanted to see the pyramids. You know, the creation scientist in me, I wanted to see the pyramids. So we flew into Mexico City, which is a city that's in a bowl with mountains around it. And when we got out of the car, the air was so dirty. I remember going like this, and it was dark on my finger from the air. And I'm on my honeymoon dressed up in a very nice white shirt. And I'm going, oh, the air is that dirty. I mean, that just freaked me out because I'm from Miami. We have clean air in Miami. I remember the first time I went to Auburn, the first 2 years I went to school, I went to Auburn University. And I remember going to a football game in Birmingham because back then Auburn didn't have its own stadium. And when we went to Birmingham and went over the mountain and started to go down into that town, my eyes started to hurt. And I remember saying to my girlfriend, my eyes hurt. And she started laughing. She goes, you're not used to pollution. I'm not used to air pollution. It gets to me. My husband and I cut our honeymoon short. We got sick from the air pollution. It made us both sick. Okay, so this is nice that they've cleaned up the air. I am telling you, you've never seen it like it used to be. And it used to be terrible. And I used to drive old muscle cars. 68 Camaro was my first car. I had all sorts of muscle cars, and they loved that leaded gasoline, and they really had a lot more power. But you know what? I'll give up all that power to have cleaner air. That's really what it gets down to, because it's so much nicer to have clean air. It really does make a difference. I just want you to know that. The carbon monoxide, go ahead, it's on page 48, is a gas that was produced from our cars also from incomplete combustion. He asked this question in all 3 classes. I don't know if he asked it in physics. He asked it in physical science and biology and chemistry. I think he must have worked on this in the industry or something. But cars used to do incomplete combustion, which means they burnt the gas incompletely and therefore produced carbon dioxide. So they put catalytic converters on the cars, and that completes combustion so that now they produce CO2 instead of carbon monoxide. Carbon monoxide is what kills you if you sit in a garage with a running car. And even if they find you, you're dead. Unless they can do a transfusion, because your red blood cells grab the carbon monoxide thinking it's oxygen, and then they can't shake it loose and you die. Okay, so carbon monoxide poisoning is very, very dangerous, and that's why these catalytic converters are very important, because they lower the amount of carbon monoxide from all the cars. In the process, though, they had to make the cars lighter, because they changed the gas and they changed the way they burn the gas, so they had to make the cars lighter. And I know, have any of you ever ridden in a 1955 Chevy or 1957 Chevy or an old muscle car like a 68 or 70 Mustang or Camaro or something? How heavy was the door?
Really heavy.
Really, really heavy. Oh my goodness, both of you are going, yeah. The first car I ever got into that was after that period of time was a Datsun. That was Nissan, just so you know. It used to be Datsun. And it was a friend's car. And I got in, and when I shut the door, I shut it like I would have shut a normal car, these older cars, and the whole Datsun went, and the guy's like, take it easy, you're going to wrench the door off. And I'm going, man, this car's a tin can. And it was compared to those old cars. When you ever get in them, you shut the doors, and that's why my parents wanted me in an old car, because I used to play bumper cars with my old car. And so it kept me alive, you know. And so they have cut down on the air pollution, because they've made the cars lighter, and that's very important. But they said that there is a cost-benefit analysis where you measure what you pay for the benefit that you receive. And what was the cost that they didn't take into account here when they made the cars lighter? Let's see if somebody knew. Anybody knew? Yes, sir.
Increase in car accidents.
Very good. More deaths in car accidents, because when you have an accident in one of these old cars, I just kept fixing my old Camaro, because you could bump into other cars, it'd dent a little bit, and you just bang it out and keep going, you know. But new cars, it's much more severe, the damage, and so people were dying from that. And so we reduced the air pollution, we made things more expensive, we have lighter cars, so more fatalities. Because of the changes that we've made. I think that the cleaner air is important, but see, now they've tried to make the cars safer again. They've put infrastructures in them to try to make them safer that are still light. That's the kind of thing they're doing. So they're trying to make it, and let's be honest, we need to not be texting while we drive. We need to not be eating our cereal while we drive. We need to be paying attention when we drive, and hopefully that'll help us to, you never heard of somebody eating cereal while they drive? Tim Hawkins does that one, and it's hysterical. But anyway, that's what made me think of it. I think he's very funny. Anyway, a cost-benefit analysis, you're going to see more of these as we go along this year, because I don't really know if you realize this, but you do cost-benefit analyses all the time. Let's say you're saving up for something. Let's say you want to buy, would you guys be saving up for a car yet? Okay, let's say you're saving up for a car. So you're saving up for a car, and you're saving and saving, and then your youth group's going to go to Rock the Universe. And you have to make a decision. Do you want to use that money towards Rock the Universe, or do you want to use that money towards your car? And you kind of have to sit down and figure out the cost-benefit analysis. Well, it'll slow me down on getting the car, but you know, you have to decide, don't you? Your parents make cost-benefit analysis all the time, analyses. They have to decide, you know, Can we afford this vacation right now? Is it worth what we'll have to give up to be able to spend the money on that? Do you see what I mean? Your time counts, your money counts. These are cost-benefit analysis. You weigh the cost to the benefit that you're going to receive, and you decide whether it's worth it or not. We're running out of time. Is it fast, Clay?
Well, I was just going to ask, would another name for a cost-benefit analysis is one that's probably a bit more familiar, would be a pros and cons list?
Maybe, yeah, maybe. That'd be one way of thinking about it, Clay. That sounds good. Yep. But he's going to call it a cost-benefit analysis, so I want you to be familiar with it that way. But yeah, you can think of it as a pros and cons list. Yes. Okay, on page 50, it says, suppose you could institute regulations that would be targeted at one specific air pollutant. Based on the graph that we saw before, which one would be the best to target from a cost-benefit view? What did you think?
The nitrogen oxide.
Yes, thank you, because it's still the one that's the highest, isn't it? All right, turn over to page 53, please. And this is to help you be ready for your test. Remember, humidity is moisture in the air. And if you need to stop me, slow me down, just raise your hand, okay? Absolute humidity is the concentration of the water in the air, water vapor. You could just say water. We know what you're talking about. Relative humidity, I've got it as a percentage. I've got a fraction. I've got water vapor in the air over maximum water the air can hold. But you could say that a few different ways. The greenhouse effect is the gases being trapped by the sun's warmth. The gases that trap the sun's warmth. I can talk. Parts per million is the parts of something in every million parts of a mixture. Number 2 says the temperature is the same at 1 p.m. on 2 consecutive days. For a person who is outside working, however, the second day feels cooler than the first day. On which day was the relative humidity higher? The first day, the one that felt hotter, correct? Did I get that right? Good. Okay, number 3. A child decides to keep his goldfish outside in a small bowl. Here in Florida, it would be full of algae in no time, wouldn't it? He has to add some water every day to keep the bowl full. On 2 consecutive days, the temperature was very similar. But on the first day, the relative humidity is 90 degrees, while on the second day, it's 60 degrees. On which day will the child add more water to the fish bowl? The second day. Very good. Thank you. Because it's a lower relative humidity, and therefore more water will be able to evaporate. Number 4, if you put a glass of water outside when the relative humidity is 100 degrees, how quickly will the water evaporate? Yeah, and it's not 100 degrees. It's 100%. I'm sorry. It won't evaporate. Very good. Thank you. Number 5, why does sweating cool people down? Remember what's happening? Very good. It takes energy for the water to evaporate, so it's being removed from their skin. Very good. Thank you. What is the percentage of nitrogen in the air? Everybody. 78%. What about oxygen? 21%. Thank you. Number 7. What would be the consequence of removing all carbon dioxide in the Earth's atmosphere, or the Earth's air supply? What would happen?
No plants.
No plants. So everything would die, and also it might make the air cooler. We don't know for sure, but it probably would. Okay. Number 8. What would be the consequence of removing all the ozone in the Earth's air supply?
The ultraviolet light would kill.
Right. Everything would die because the ultraviolet light would get through. Very good. Thank you. Number 9. What would be the consequences of a sudden increase in the concentration of oxygen in the Earth's air supply? What would you have if you had higher concentration of oxygen in our air supply?
A lot of lung problems, and you would go blind.
Okay, so physical problems, lung problems, blindness. What's one other thing we'd have? Forest fires would increase, and that would be bad. Thank you. We don't think of that a lot, but that is a real problem in a lot of places. Number 10. Suppose astronomers found another solar system in which there was a sun just like ours. Suppose further that a planet in this new solar system was just as far from its sun as is Earth from our sun. Since the vast majority of energy that planets get comes from their sun, is it reasonable to assume that the new planet would have roughly the same average temperature as that of the Earth? Why or why not? What'd you say? Yes?
No, because it may or may not have an atmosphere.
Very good. No, because, and it would have to have an atmosphere similar to ours, actually, to have a temperature similar to ours. We haven't learned about it yet, but Venus has a real heavy-duty atmosphere that has so many greenhouse gases that it's hotter than Mercury. even though Mercury is closer to the sun. Venus is the hottest planet because of its atmosphere. 858 degrees Fahrenheit at its surface. Yeah, it would melt lead, literally. Number 11, what makes up the majority of the air? We exhale.
Nitrogen.
He's going to ask you that several times in your lifetime. Okay, so I just want you to know that. Do we exhale more carbon dioxide or more oxygen? Oxygen. Do the data indicate any significant global warming?
No.
No. If you say yes, then I want you to say 1.2 to 1.7 degrees Fahrenheit. I mean, be specific. Otherwise, say no. And that's since 1880. 14, the current concentration of ground level ozone is 0.110 ppm. What is the percent? So you're going to go 0.110 ppm times line. You put the parts per million down here, the percent up here. This gets a 1, this gets a 10,000. Remember, when you do this in the calculator, you're going to go 0.110 divided by 10,000 and give your answer in percent. Okay? So it's like 0.0000110%. Wow. 15, suppose you had a sample of air which the concentration of nitrogen oxides is 0.023%. What is the concentration of nitrogen oxides as expressed in ppm? And so it's the reverse. So you have 0.023% times line, the percent down here, the ppm up here, and so this gets the 10,000. And so we're going to move this decimal place back a bunch of times.
230.
There you go, 230. Thank you. Let's see. 16, is the air cleaner today than it was 30 years ago? Yes, definitely. It's cleaner today. And the cost-benefit analysis he asked you there, remember you are deciding whether the cost, the benefit you get is worth the cost you'd have to pay for something. What does a catalytic converter do in a car? You could say it completes combustion. You could say that it converts carbon monoxide to carbon dioxide. You pick. What do scrubbers do on a smokestack? They absorb the sulfur oxides, so they lower the air pollution. Or you could say they help with the air pollution on the sulfur oxides. Your choice. In the United States, many regulations aimed at decreasing the amount of ground level ozone in the air because the ground level ozone is considered a pollutant. At the same time, many regulations are aimed at increasing the amount of ozone in the ozone layer. Despite the fact that ozone in the ozone layer is the same as ground level ozone, ozone in the ozone layer is not considered a pollutant. Instead, it is considered an essential substance. Wow. Wow, that was a long way to go around the barn to get the horse in. So why do we need ozone? What does it do for us? What does ozone do for us? Why do we need ozone in the ozone layer? Go ahead, Carter.
Protect us from dying.
Yeah, what does it protect us from? Do you remember?
Blind.
Somebody help him.
UV rays.
Ultraviolet light, UV light. It protects us from ultraviolet light. Thank you. Very, very good. All right, you guys. So you're going to study this. You're going to take this test. And you're going to read the first half of the next chapter, right? Okay. Have a good week.